All right. My clock says 2 o'clock. Actually, it says 1 o'clock. What time is it now? 2 o'clock. Okay. Yeah, 2 o'clock. Okay, so the trip was really good. So I went to a conference of people who do this job just like me from all over the country. It was really, really fun. Turns out teaching computer science is a really rewarding and stimulating thing to do with your career. So, because at least I enjoyed meeting all these people and seeing all the different avenues that all the different perspectives that they bring to not only being computer scientists themselves, but to mentoring students. So I kind of like this job, in case you wondered if you wanted to pursue this path. It's a good one. And Seattle's awesome. All right, so I'm feeling a little bit lost. As far as I could tell, you guys had MP4 due, yeah? MP4 was due. MP5 is in your pockets. You've now got it. Even though spring break, you're kind of thinking, I'll get to that at spring break. I actually recommend that you read through the spec first, just to give yourself a heads up into what MP5 looks like. Also, the extra credit deadline comes before spring break, so we don't want you to spoil your spring break working on the extra credit part. We want you to do that this week. And then we're right in the middle of exam 4. So that's what I know about sort of our administrative status. For some reason, Wade said I should talk about that. You guys explain to me why. What did you do while I was gone? Actually, he didn't say that. I won't pin that on him. What did you do while I was gone? Yeah, Neil, tell me. You learned how to remove a node from the binary search tree. Did you learn how to insert nodes in the binary search tree? Yeah. So at this point, so you learned about binary search trees, yeah? All right. Is that one a binary search tree? Yeah. Is it? Tell me what you did. Somebody raise their hand and describe what they did to convince me that that's a binary search tree. Called 26 the root, and what else? So 26 is the root, and what else is true of that structure? Yeah? Okay, so check to see whether the left child is less than the root, is less than the right child. Is that enough? Change that 23 to a 123, and it would still satisfy that condition. So that's a great start on the description. What else must be true? Yeah, Mark, you want to go? Okay, very good. I'm going to change only one word. I'm going to say descendants instead of children, okay? Because it's children and grandchildren and great. All right. All right. So everything in the left subtree is less than the root. Everything in the right subtree is greater than the root, and that's true recursively, okay? Is an empty tree a binary search tree? Yes. All right. As fast as you can. So I agree with you that that is a binary search tree. As fast as you can, do an in-order traversal of it. 4, 8, 23, 26, 47, 50, 62, 70, 98. Yeah? What did you have to do? All you have to do is just sort of say those numbers in increasing order, because that's what an in-order traversal will get you in the context of a binary search tree. We could prove it, but we're not going to right this second. Okay. Uh-oh. Oh, pretty. All right, I need for you to tell me a key that I could enter that would be in 4's left subtree. I need a positive key that would be in 4's left subtree. 1, okay? So I'm going to insert 1 here. If I can keep a steady hand, insert, come on. Fine. Insert, click. Oh, come on. Please. B-I-S-U-A-L, go. I think it was this one. Was it this one? Yes. Okay, good. Okay. We're not there yet. We're doing binary search trees. Okay, so let's click out of that. Let's insert, oh, this is much more interesting. I need a key that's in 50's right subtree. 50's right subtree? Yeah, it'll be in 50's right subtree. Somebody raise their hand and give me a key. Yeah? 53. All right, now what I want you all to do is look and make sure you know, or you have a really good guess, where 53 is going to be. Okay, where do you think 53 is going to end up when you insert it into this structure? Ready? Do you have a further description? Somebody describe it. Raise your hand and describe it. Yeah? Yes, you. 58's left subtree. That, to the left of 58. Okay? Yeah? Yeah? Yes. Okay, good job. All right. So now I want somebody to tell me where, let's see, where would 75 go? Somebody describe for me where 75 would end up. Where does 75 end up? I shouldn't walk all the way over here. 75 goes where? Come on, really? Okay, I don't want to insert 93. I want to insert 75. I think it's going to go, so I don't know where 75 goes, but it has to be in 67's right subtree, right? I don't know where 75 goes, but it has to go in 96's left subtree. I don't know where 75 goes, but it has to go in 73's right subtree. I don't know where 75 goes, but it has to go in 80's left subtree, and oh, look, there's a spot for it, okay? So that's where it's going to go. Is that clear for everybody? Go. No, really, go. Okay, okay. Yay! All right. Any questions at all about inserting into a binary search tree? Yeah? Should it have been inserted between 73 and 80 is the question. Yeah? Did I restate that question correct? Could we? So it would be reasonable to look at that tree and go, look, we could have put 75 right in there if we wanted to. That's not how our particular algorithms work. And I assert that if there were any branching at all that happened between them, it would get more complex to do that. So we're going to always do insertions at the bottom. Okay, we're always going to be replacing a null. Any other questions about this? All right, I want to know in the search for value 57, how many keys do I need to look at? So if I want to know if there's, hey, is there a 57 in the tree? How many keys do I need to look at? Raise your hand with the number. Is there a 57 in the tree? I want to know how many keys you have to look at. Hi. Yeah, that many, right? Let's see if that's true. I want to do a search for 57. Go. Really go. 1, 2, 3, 4, 5. Wasn't there, okay? So the code that's shown on the right would return null. All right, any questions at all about binary search trees? Yeah? Oh, I don't know. Probably they're unique keys. It's a good question. And so the question is, what happens if you insert duplicate keys? I don't know what this applet does or what this application does. If you were using your binary search tree to implement a dictionary, then it would either do nothing or replace the value that was already there. If you did it a slightly different, if you were using your structure for a slightly different thing, you could put the duplicate value in and just say that it goes either to the left or to the right, but always the same of its duplicate key. So you'd have a less than or equal to instead of a less than in the comparison. All right, I've got one more thing to try. I don't know about you, but that 50 is really bugging me. Is it bugging you? No, the 50 is bugging me the very most. Oh, I haven't used this applet for this, or whatever this thing is. But all I know is I want to get rid of, oh, you ready? I'm going to slow this down even. Might be too slow. We'll see. Go. Okay. So we're searching for 50. Oh, look, we found it. Uh-oh. Oh, this one does the wrong thing. Whoa, what? Whoa. What? Is 67 bugging you? Should we watch and talk aloud? All right. So suppose I'm going to remove 67 from the structure, okay? Now, I can, if I remove 67, the tree falls apart, right? Falls apart. But I can plug the gap with either of two values. Which two values could be used for 67 without destroying the order of the tree? If I remove 67, the tree falls apart. How could I glue it back together? What could I use? Either 61 or 73, right? Values from the tree that could be used to glue the tree back together. In the algorithm that you talked about last Friday, you would have chosen 61 to be that glue. This applet, whatever it is, application, this toy, chooses 73 instead. It chooses the number that comes after 67, the one you're removing, in order. Okay, does that make sense? So let's try that one again. Try the removal. Remove. Really, come on. I want to remove 53. I want to remove 67. Go. Okay. Search for it. Found it. Uh-oh, I'm looking for the glue. Oh, look, I found the glue. All I have to do is pull that value up and reattach what was below it. Okay? And I think you went over the code to do that on Friday. Any question about it? Is it okay? All right, so we've actually looked at all three of the dictionary functions. All right. I'll try to remember to put the link to that applet on the website so you can play around with it a little bit if you like. It's not that one's broken. It's not the one on your, like, that one doesn't exist anymore. The Cumatica one doesn't exist anymore. The one on your slides, which is from Harvey Mudd, that one requires Java, so it makes you swear. And the one I just did, I hadn't used before. So I'll put the one I just did as the link on the web page. Okay, so here's what I want you to do. As you know at this point, binary search trees are built up by a sequence of keys to be inserted one by one. That's how we build it. And we do it in such a way that we always add a new key to an empty spot. So what I want you to do very quickly is go ahead and do these insertions in sequence. And I need somebody to do it for me on my tablet. I need a volunteer to do it on my tablet. Okay. Okay, so build a tree out of these. And be sure and copy off of the person sitting next to you. There was a talk on plagiarism at my conference. The biggest takeaway is that plagiarizing people's MPs hurts your grades, your exam grades. That was the biggest conclusion for the paper. Just FYI. Overtly. Oh, guess what class the research was done on? Class. We didn't do the research, but it was our data. Not this year, from past years. Okay, yeah, this is good. All right, do you guys like this? You like this tree? So what characterizes, first of all, do you like this tree? So good job, Bart, first of all. It's exactly the right thing. Look, it's the same one you got too, right? So it's the right tree, but do you like that tree? So what don't you like about it? What don't you like about it? Yeah? Right. If you need to use this tree at all, you're effectively doing as he said. What's your name? What Alex said. You're doing a linear search. In fact, if you tilt your head a little bit, not even very much, this looks like what? What does this look like? A linked list. That's right. So what is it that characterizes the data that created this thing? What's special about the data? What's special about the data? It's in order. Very good. Very good. Okay. So you go, okay, look, inserting in order into a binary search tree makes ugly trees. And when I say ugly, I mean tall. You could write tall down if you want to do ugly equals tall. And the reason for that is because all of our algorithms depend on the height of the structure for their execution. Right? In the worst case, we're going to navigate the height of the structure. All right, so is this one the only ugly one? If I said make the tree by inserting these bottom to top, we'd also have an ugly tree, right? So either monotonic increasing, which makes the tree like this, or monotonically decreasing values, which would make the tree like this, those are both ugly, okay? All right, fine. Well, maybe that's rare. Maybe that's rare. You like this tree? Same story, right? It's still kind of stringy. How about stringy instead of tall? All right, so what I want is a sequence of insertions that would create a tree like this. And Bart, you can hand off my tablet to whoever you like. Right, so you guys go ahead. Think of a sequence of values that you could insert so as to build a tree that looks like that red one, the one with the red vertices. make this an 87. Make this an 18. You see why? Make sure you see why. All right. Okay. So everything to the right of one is bigger than 1. Everything to the left of 87 is less than 87. Everything to the right of 2 is bigger than 2. Everything to the left of 22 is less, etc. Okay? I could test it by doing an in-order traversal and making sure that the values were in order at the end, that I printed them off in order, but it looks okay to me. All right, so this one looks a little stranger, right? And if I had given you these values as a sequence of insertions like this, it would have been a little bit harder to identify the fact that those are of they create an ugly tree. Now, what I want to know from you now is, if I tell you that there are n items in a tree, so for this tree n was 6, for that tree up there n was 5, it looks like. If I tell you there are an arbitrary number of elements in a tree, what I want to know from you is how many bad ones are there? That is, how many trees are there that are as tall as possible? You can pass my tablet to anybody that you like, including me if you like. Yeah. Okay, and I want you to peek at, I'm asking you these questions. I want you to peek and see if your neighbor has written anything at all. Wade, you can pass it too if you'd like. You can pass it back to me if you like. Thank you. No, I'm sorry. All right. Anybody have a hypothesis about this? Yeah? Yeah. At least 4. That is definitely true. Okay, 4 trees of height 2, I believe that's true. Okay, I buy it. Yeah? Yeah, okay, so at least n. Yeah, at least n. Yes, I agree. Okay. Yeah, Alex? Whoa, what? You guys hear that? Okay. So the answer is 2 to the n minus 1. Now, I think some of you are going to be surprised at that. The other two guys were not wrong because it's at least, right? My question is, how do we justify this? How do we justify this value? Why do you go, oh yeah, that makes sense? And what I want to point out is that this is a choice of going to the right, right? This is a choice to the right. This is a choice to the left. This is a choice to the right, the left, the right. Okay, now do you see why this is 2 to the n minus 1? Look at this tree. That was a right followed by a whole bunch of lefts, right? So effectively, what I'm doing is making n minus 1 binary choices, n minus 1 binary choices, okay? Any question about that? So you see, whoa, okay, that makes sense. Alex, what were you thinking about when you noticed that it was 2 to the n minus 1? Yep. Yep, very good. Exactly right. All right, any other questions about this? Yeah? Yeah, so he's pointing out that if you know your data already and you start with 2, for example, then you have changed the number of ways that you can do it after you've chosen one from your given list. So we're not going to focus on values at all. Okay, so we're really just looking at the structure of it. And if you have n data elements, then you can create 2 to the n minus 1 different trees by arranging them in particular ways. Okay, so there are lots of random arrangements that could come to you where you'd go, whoa, that stinks because it made a tall tree. Does that make sense? All right. Any other questions about this? Other observations? So is this a big number or a small number relative to n? It's a really big number relative to n, and so we are a little bit worried that using binary search trees as a mechanism for storing a sequence of data is maybe not really any better than linked lists. Okay, so we should have anxiety over that. We should be worried about it a little bit. All right, so let's see what that looks like. Anytime we are worried about something, we want to start looking at it mathematically. And so in the context of this situation, we want to analyze pretty robustly whether we should be worried. So here's what we're going to do. We understand that all of our algorithms run in time proportional to the height. But you know what? Nobody on the planet wants to hear about your algorithm in terms of the height of some structure. Algorithms are always valued by how they do on the amount of data the structure holds. That is, we want an argument about n even though our algorithms run in time proportional to h. Does that make sense? So our algorithms do one thing, but our structures hold n amount of data. We need to reconcile the two. The way that we're going to reconcile the two is from 2 directions. We're going to put both a lower bound on h. That is, h will always be bigger than some function of n. And what this means is that no algorithm our algorithm cannot do better than this function of n. Okay, because h will be at least that big. So height-based algorithms can do no better than f of n. Okay, and the other direction from which we're going to look at this is from the upper bound. And the argument here is simply that no height-based algorithm should do worse than g of n. So no height-based algorithm than g of n. Okay, so we're putting both an upper bound, we won't go worse than this, and a lower bound, we can't do better than this. F of n, g of n. All right, instead of drawing a picture, I'll do the arm dance thing. Multimedia here. All right, any questions about all that? All right, just as a reminder and kind of an aside, the height of a tree is what if the tree is empty? What are we going to use by convention? -1, that's right. We're going to use -1. That'll actually be more useful to us. Well, it'll be useful to us here too. Okay. All right. We are going to prove these things, especially the first one, especially the lower bound on the height. The upper bound is pretty easy. Okay. Ready for this? I'm not ready. I'll tell you this flat up. Arguing this lower bound is a pain in the neck. You have to take logs. It's really easy to have off by 1 hour errors. There's floors and ceilings, and I hate this proof. So here's what we're going to do instead. Instead of proving that h is greater than or equal to f of n, this one makes me, that's like an ultimate frowny or something, okay? Oh, I know. Here. There. Instead of that, I want to make this argument instead. I'm going to say that n, for any tree, the number of nodes in it, is less than or equal to the inverse function of its height. Because from that I can make my argument. From that I can make the argument that I really want, which is one about the algorithm. Okay? And it turns out that this is easy peasy. Okay? All right. Very common trick. The characteristics of the functions that allow you to do this are that they are invertible, and in this case, they're monotonic too. Okay, so rather than think about lower bounds on h, we're going to put upper bounds on n. I'm going to hypothesize a function called m. So here, capital M plays the role of that inverse function. Okay, m of h. And I don't know what this function looks like, but it's going to represent for me the very largest number of nodes that you can have, the very greatest number of nodes that you can have in a tree of height h. So this is the max number of nodes in a tree of height h. Okay, it's parameterized by h instead of n. All right. Well, our smallest height that we care about is m of -1. What is that value by definition? What's the maximum number of nodes you can put in a tree of height -1? 0, that's right, very good. And m of h, for h greater than or equal to 0 or greater than -1, I don't know. I don't know what this value is. I better think about it recursively, right? So give me a description of the maximum number of nodes I can put into a tree of height h. Yeah, it's a binary tree. It's a perfect tree, just in case you're kind of thinking about it. I know I've got 1 for the root. Tell me about these guys. How many nodes can I put in them? Oh, don't think so hard. Do it in terms of m. M is your symbol for the maximum number, right? M is your symbol for the maximum number. So it's 2. I'm trying to put the most number of nodes I can. So it's 2 of them, left and right are the same. And how many do I have in each one? M of h minus 1, that's right. Yay, okay, I've got this nifty recurrence. I don't want this in the form of a recurrence. Okay, what's the answer here? Somebody raise their hand and tell me. Somebody raise their hand and tell me what's the closed form for this recurrence. I'm ready. Yeah, Luke? Good. Okay. It's 2 to the h plus 1 minus 1 for h greater than or equal to -1. Okay. Do you believe that? Do you believe him? Do you know him? If you don't know him, you should not trust him, right? You shouldn't just go around asking people to solve your recurrences for you. Now, I trust him, but you don't have to trust him. How would you prove to yourself that he is correct in his closed form? Would you get out your capital sigma and start doing sums? Would you? Would you? What would you do? Yeah? Good. Right. Look, you guys, this is begging to be proven by induction. In fact, this is such a straightforward inductive proof that I'm going to do what's called a back of the envelope induction. The front of the envelope that you're not going to see is the explicit description of the inductive hypothesis, because it will be completely clear when we should apply it, okay? So first of all, let's do the case where, so what you guys call the base case, with h equal to -1. The definition says m of -1 equals 0. The closed form gives m of -1 equals 2 to the 0 minus 1 equals 0. Yay. Yay, Luke. He got his base case, okay? We're happy with the base case, okay? The general case, or the inductive case, is h greater than -1. Greater than or equal to 0 is kind of more pleasant. We have m of h equals 1 plus 2m of h minus 1, which equals, all right, here's our special moment. I'm going to do a little bit of algebra. It's 1 plus 2 somethings. And my question is, what goes right here and why? Notice that I'm simply asking you for substitution for this. What goes here? Yeah? 2 to the h. I'm going to write it as -1 plus 1. Is that okay with you? I know you don't like it, but is it okay if I do it like that? Okay. And then, is that it? 2 to the h minus 1. Very good. Because, and if I were to say by y, why can we do that? Yeah, inductive hypothesis, which we've written out very clearly on the other side of the envelope that nobody ever sees. Okay? All right. And that comes from the assumption that the theorem holds for smaller values. So this is true for smaller values. Is h minus 1 smaller than h? Do this. So we get to use it. Okay, and now, yay, I think we're home free. There should be some parentheses here. Looks to me like this is going to be 2 times 2 to the h, or 2 to the h plus 1, and then I've got minus 2 plus 1. Phew, yay. Okay? Any question about that? Now, let's argue for a second what we just did. We just showed that n was less than or equal to 2 to the h plus 1 minus 1. Yes? That's what we just argued, because this part is m. This part is as big as it can possibly, as big as n can possibly be. It's an upper bound on n. That's how we defined m. It's the biggest number. So our true value, n, has to be less than it, right? But now, you know, when did you learn to do this? Is this Algebra 1 maybe? Now we're going to turn this around. Now we're going to turn this around and get, oh, this implies, oh, well, I'm going to do n plus 1 is less than or equal to 2 to the h plus 1. And then what? take logs. So I'm going to have h plus 1 is at least log of n plus 1, or h is at least log n plus 1 minus 1. Yeah, we're all good so far? Look, blur your eyes a little bit. H is at least log. Okay, I know there's some other stuff here, but remember we're talking asymptotic behavior. And remember that the definition of big O gives you this constant factor. Well, big O, though, has the inequality going the wrong way. Here, we still can get rid of the constant factor and or ignore the constant factor, and in fact what we're looking at here is that H is equal to, anybody want to say it? Because it's cool if you know it. Not big O. You know what the other one is? You guys do lower bounds in 173? Okay. So this is our symbol for, this is our symbol for greater than. This is our symbol for lower bounds. Okay, so big omega, but it means kind of the same thing. Is this good news? Oh, except that it's wrong. Nope. All right, so here's the conclusion. Somebody comes along and says, I've got a binary search tree insertion algorithm and it runs in time, constant time. What do you say? What do you say? It can't, right? It certainly can't build trees the way mine builds trees. It might be able to insert, but it doesn't make a binary search tree. Maybe it puts everything at the root, right? In constant time. That's not a binary search tree. So this says all height-based algorithms will run in time no better than log. Okay? All right, any question about it? So this is kind of a piece of, well, I don't know whether this is good news or bad news. It's just news. Real news, by golly. It's not fake news. Who said that? We'll talk about that later. All right, math. Well, maybe math could get you fake news. Well, this is not probability. This is like, all right, though probability will come up later. All right, fine. What's the worst? So now we've put our lower bound on the heights. What's our upper bound on the heights? Well, I think it goes without massive argument to say that the very tallest tree we can make from n elements has height n minus 1, right? So in this case, we would say that the height of our tree is always less than or equal to n minus 1 for n pieces of data. Again, if you blur your eyes and give yourselves all the constants that you need, this is equivalent to saying H is big O of n. That is, it's bounded above by n. I have more stuff to tell you. You're missing out. Bye. All right. Lower bound, log n. Upper bound, n. Good news or bad? It's hard to tell. It's a little closer to bad because it's still feeling like linked lists. All right. Ooh, I got a ways to go. Okay, so here's the deal. The height of a binary search tree depends on the order in which the data is inserted into it. So for example, there's two sets of data right there, and the two trees that they build are very, very different. In fact, the height of that first tree, I believe, is 5, and the height of the second tree is, I believe, 3. 4 plus 2 plus 1, 4 plus 2 plus 1, 2, I believe. Yeah. 1, 2, 3, 4, 5, 6, 7. Yeah. So these two data sets that are the same gave us completely different tree heights. Now, how many different ways can you arrange n pieces of data? How many different ways can you arrange n pieces of data? N factorial, very good. N factorial. Your data can come at you n factorial different ways. If you built the heights of all of those n factorial trees and you took the average tree height, you would get any guesses? A big O of, what would you like me to say here? So on average, the tree height is going to be, what do you hope I say? Log n. You hope I say log n. I love when I can tell you what you want. Big O of log n. So on average, if you can assume that your data is coming at you, the data that you use to build this tree is coming at you in some random way, then you can assert that binary search trees are probably going to be have height log n. Now, I want to do better than that. I want to make worst case assertions because this is just sort of a if you're lucky or if you're not unlucky, right? If your data isn't organized in some way. All right, so let's fill out this table really quickly to so as to look for where we can improve things. I just told you that on average, for each of all the height-based algorithms, you get log n. We argued earlier that for height-based algorithms, worst case was big O of n. What's the worst case for insert, remove, and find on a sorted linked list? Sorted linked list. Worst case. Big O of, they're all the same, so I'm just going to, big O of n, that's right. You got to go looking for the right spot, right? You have to find the right spot. How about finding in a sorted array? O of, finding a key in a sorted array. Tell me where 17 is. Not the index, the key, the value. It's sorted. These are big O of n, I know, because of shifting. But this one, for finding, it's sorted and log n, good. Why? Binary search, here. All right, little BS here. Oh, probably shouldn't. Okay, that was stupid. I apologize. All right. What's the running time for traversal in all of these things? Running time for traversal? Traversal is always going to be big O of n, okay? All right, so where's the room for improvement, really? What about this is giving us the excuse to spend 2 weeks of class on this stuff? We're going to work on this part, okay? We're going to spend some time seeing if we can do better there. And I have a minute. I have a minute. Which of those trees do you like better? The one on the right, right? Yes. Okay, you like this one because it looks more like a mountain. And we all love mountains. Okay? This one we describe as a stick. Okay? We like sticks too, but not as much as mountains. All right. And no, I got to give you the definition. This is okay, okay? So first of all, I'm going to give a height balance to a tree by taking the difference of its left and right subtrees, okay? So the difference in the heights of this mountain, of its left and right subtree, what's the difference in their heights? 0, right? They are the same height. How about the height balance of 50? What's the difference in the heights of their subtrees? It's 2, right? Or the absolute difference is 2. That is, one is 2 elements longer than the other. So this one has height balance 2. I also have this backwards. It's supposed to be right minus left, I believe. Okay, so this one has height balance 2. This one has height balance 0. A tree itself, we say, is height balanced if we're going to put a constraint on the metric if the tree is empty, or if it's not empty, the absolute value of B is height balanced if the absolute value of B is, you want me to say 0, right? But if it's 0, we're very constrained in our tree, the trees that we can build. In fact, perfect trees are the only ones that we can build. And so what we're going to do is allow a little bit of mush on the balance factor. And then we're going to add the constraint that the subtrees must also be height balanced. And TL and TR are height balanced. Okay? All right, any question about that? Okay, next time we'll talk about this tree. Hey, what's up? What does the F of M, G of N mean? They're just functions.